Did you know Mars was once covered in rivers and lakes? A world that might have hosted life long before humans even existed. You drift effortlessly through the quiet of your vessel, the faint hum of distant engines, a soft lullaby against the endless dark. Ahead, the red planet glows faintly in starlight, its thin atmosphere barely holding on, its surface cold and silent. And yet, somehow, you can feel traces of the warmth that once was in ancient rivers carving paths through dusty plains, a ghost of life that might have been. Our probes, those tireless robotic explorers, have uncovered layer after layer of Mars' secrets. Each mission teaches us something new, yet Mars always seems to ask more questions than it answers. You find yourself staring out the window, wondering if this quiet, red world really was a home once, imagining the first sparks of life in a place now so still. Think of Giovanni Schiaparelli in 1877, mapping Mars by hand, convinced he saw canals, or Percival Lowell decades later, certain those lines meant intelligent life. Their hope set humanity on a quest that continues even now. By 1962, the Soviets tried to reach Mars with their Mars M1 flyby. It failed, fiery disappointment lost in space. Yet ambition never quit. In 1971, NASA's Mariner 9 finally entered orbit, only to be swallowed by a planet-wide dust storm, its cameras capturing little but swirling red chaos. Soon, Soviet orbiters joined, carrying their own landers, each one silently circling, waiting for Mars to reveal its secrets. And here you are, floating gently past it all, feeling the calm of space that those early pioneers never knew. 1. The Mars 2 lander met a swift and fiery end, crashing into the obscured surface. The Mars 3 lander, however, miraculously made it down intact, only to transmit one garbled, ghostly image before falling silent forever. Now, you had 3 spacecraft patiently circling, all staring at a seemingly featureless, dusty, red sphere. The Soviet probes were programmed for immediate action, but the American Mariner 9 held a crucial difference. NASA could command it to simply wait. Imagine that patience, waiting for months, for the storm to subside, for Mars to reveal itself. And reveal itself it did. Slowly, majestically, the thick atmospheric shroud began to clear, unveiling wonders. Mariner 9's patient gaze was rewarded with the first sight of 3 distinct craters towering above the lingering dust. These were no mere craters, but the majestic summits of giant volcanoes on a region now known as the Tharsis Plateau. Soon, a tapestry of complex geological features emerged from the haze. In some areas, the surface was heavily cratered, a stark reminder that the vigorous tectonic forces that constantly renew Earth's surface were absent here. The colossal volcanic activity, responsible for forging the solar system's largest mountains, had ceased billions of years ago. This patient vigilance allowed scientists to meticulously construct the first accurate global map of Mars, laying the groundwork for future landings, including the Viking probes in 1976. You feel a soft shift in the recycled air, a quiet breath within your ship as you recall the next chapter. The Viking 1 and 2 missions, twin orbiters and landers, gracefully touched down on the Martian surface, returning the very first intimate portraits of the Martian landscape. Their primary directive, the driving pulse of the entire program, was to seek out any telltale signatures of life. But even with their sophisticated instruments, researchers now understand the limitations of those initial experiments. As we on Earth began to explore the tenacious life forms thriving in our own planet's most extreme environments. The question of where life might exist on Mars began to evolve, to deepen. Yet, at that time, the scientific consensus hardened. Mars was sterile. The hopeful whisper of Martian life seemed to die, at least for a while. A long, quiet, two-decade hiatus followed, a period of introspection and technological evolution. Then, in 1996, a new chapter began as the Mars Global Surveyor gently slipped into orbit. The images it transmitted back were astonishingly clear, far surpassing anything seen before from the red planet. While earlier orbiters had focused on broad mapping, the Global Surveyor delivered high-resolution views that brought ancient Mars vividly to life. You can almost see them now, detailed riverbeds, even the delicate branching patterns of long-dead river deltas etched into the ruddy surface. Yet, the occasional, perfectly formed impact crater scattered across these ancient water systems told a different story. Nothing had flowed here for billions of years, a world preserved in amber, a testament to a long-vanished past. Just a year later, in July of 1997, another intrepid explorer arrived. The Mars Pathfinder was part of a bold new philosophy from NASA's administrator: faster, better, cheaper. The idea was to streamline development, slash budgets, and while acknowledging a higher risk of failure, the reduced cost meant the potential for more missions. Pathfinder's task was to deliver a small rover to the surface, and to do this, it employed a radically new airbag landing technology. Imagine, essentially, a gigantic cosmic bounce house, borrowing safety concepts more from automotive design than traditional spaceflight. The chosen landing site, Ares Vallis, in Mars's northern hemisphere, was notoriously rocky, but thought to be safe enough. It was believed this area held a broad array of rock types, evidence of an ancient, colossal flood. The innovative technique worked flawlessly, a spectacular proof of concept for future missions. The Pathfinder wasn't just a landing craft. It transformed into a sophisticated base station upon arrival. Its 3 solar panels unfolding delicately, like petals unfurling in the alien light. It bristled with sensors, diligently measuring atmospheric pressure, temperature, and wind speed, constantly relaying its findings back to Earth. But its most captivating cargo was the little Sojourner rover, a tiny 6-wheeled explorer that set out to investigate the immediate surroundings. Sojourner, equipped with cameras and an alpha particle X-ray spectrometer, became a global sensation. It was the first mission to have its own dedicated website. It beamed back thousands of images and invaluable data about Mars's atmosphere and geology. Its overwhelming popularity wasn't just a fleeting moment. It guaranteed an exciting future of even more Mars missions. And just like that, Mars was back in vogue, its mysteries once again drawing us in. Then, on a crisp morning, April 7th, 2001, another silent sentinel was launched, the Mars Odyssey orbiter. It carried 3 primary instruments and, crucially, had the ability to serve as a vital relay satellite, a cosmic bridge for all future surface missions to communicate with Earth. Upon its arrival at Mars, it employed a truly ingenious new technique to settle into orbit. After a relatively brief burst from its engines, Mars Odyssey entered a highly elliptical path, its closest approach skimming the planet's incredibly thin upper atmosphere. This brilliant maneuver, known as aerobraking, allowed the craft to slowly, gently circularize its orbit over a period of 3 months, saving a remarkable 200 kilograms of precious fuel. Clever, isn't it? Using the planet itself to slow down, like a whisper in the wind. This quiet, persistent probe is still diligently working today, a testament to ingenuity and endurance, a constant eye watching over our red planet. As the subtle hum of our own vessel softly vibrates through the floor beneath you, echoing the silent dance of distant stars. Imagine the era when Mars truly began to unveil its secrets. For years, Earth kept its gaze fixed on the crimson planet, each mission building upon the last, like layers of stardust settling on a long-lost dream. Then, in December of 2003, a fresh whisper of ambition reached the red world from the European Space Agency. Gracefully launched by a Russian rocket came Mars Express, their inaugural planetary explorer. You might feel a gentle pull as your own ship subtly adjusts its orientation, mirroring that distant journey. Mars Express arrived with a companion, a tiny lander known as Beagle 2, though sadly, its voice was lost to the Martian winds. Yet, the main orbiter persevered, a tireless messenger sending back invaluable data, so much so that its mission has been extended repeatedly, its journey stretching beyond expectations. From your console, the soft, ambient glow reflects tiny flecks of cosmic dust dancing in the recycled air as you visualize the stunning 3D panoramas it sent home. Sculpted from its higher resolution stereo camera, its gaze peeled back the planet's icy layers, revealing a curious blend of frozen carbon dioxide and water ice at the poles. Just imagine that, a frozen alien wonderland. But it was in the Martian atmosphere that Mars Express truly startled us, first detecting hints of methane, then ammonia. Both these gases are fleeting, quickly broken down by sunlight, meaning there must be an ongoing source, a continuous whisper of activity on the planet. While they can sometimes be formed inorganically, these molecules are more often linked to life itself. Isn't that just like space? Always offering tantalizing possibilities just beyond reach? You might need a moment to just float here, letting that thought drift through your mind like a wisp of nebulae. Barely a month after Mars Express settled into orbit, a new pair of emissaries from NASA began their descent towards the red planet, a duo of identical craft arriving just 3 weeks apart. You feel the gentle sway of our ship, almost as if you're witnessing their delicate ballet from nearby. These were the Mars exploration rovers, affectionately named Spirit and Opportunity. Spirit, the first to touch down, aimed for the expansive Gusev crater, while Opportunity sought out the intriguing Meridiani Planum, a world away on the opposite side of Mars. Though considerably heavier than their Pathfinder predecessor, they embraced the familiar, quirky bounce landing technique, enveloping themselves in protective airbags. Both landings were textbook successes, each craft settling precisely on target. A collective breath was held across the vastness of space. After a moment, as if stretching after a long journey, each craft righted itself, detaching from its protective shell, and began the autonomous, deliberate unfurling of its solar panels and camera mast. Back at the Jet Propulsion Laboratory, on a distant blue marble, the team waited in hushed anticipation for signals. Those vital confirmations that took a nail-biting 15 minutes to traverse the cosmic distance. Many had poured years of their lives into this endeavor, and now the true adventure was finally beginning. You can almost feel the collective relief rippling across the void. These resilient rovers were initially designed for a mere 90 Martian days, or sols, as the science team affectionately called them. Given that a Martian day is just a bit longer than an Earth day, mission designers, acutely aware of Mars' infamous dust storms, fully expected the rover's solar panels to eventually succumb to a layer of grime, silencing them forever. But, Mars had a surprise in store. The planet's capricious winds often swept the panels clean, granting them an unexpected reprieve. Soon, opportunity, exploring its new home, sent back undeniable proof: stratified rock patterns in Meridiani Planum, hinting at ancient sedimentation, alongside specific distributions of chlorine and bromine that whispered of a past as a salty sea. This was it, confirmation of liquid water. In April 2004, the initial 3-month mission for the rovers was extended to 8, a decision that would become just the first in a long series of improbable extensions, testament to their astonishing tenacity. The very air around you seems to hum with the echoes of their incredible journey. Each rover carried an ingenious abrasion tool designed to gently grind away a rock's surface, exposing pristine layers for analysis. Spirit first deployed this marvel on a rock aptly named Adirondack in Gusev Crater, a pioneering moment in planetary geology. The researchers agonized over using it, knowing the energy it drained from the rover's precious budget, but the payoff was immense. The rock, composed of olivine, pyroxene, and magnetite, bore a striking resemblance to Earth's volcanic basalt. Later, when Spirit's right front wheel seized, engineers devised a clever reversing technique, using a duplicate rover back on Earth, allowing Spirit to drag its inert limb, leaving a furrow in the soil. This unexpected gouge became a new research area, revealing white and yellow deposits within the trench, various salts that form only in the presence of hot water. On Earth, hot water environments often teem with microbial life. Spirit valiantly limped on for another 3 years, a testament to its engineering and determination, before finally becoming hopelessly mired in loose sand. Despite tireless efforts with its replica, nothing could free the intrepid rover. Spirit was ultimately declared a stationary research platform, its solar panels tragically unable to orient for optimal light. The last faint message from Spirit arrived in March 2010. Opportunity, however, continued its odyssey until June 2018, its long journey ending only when its solar panels finally succumbed to an insurmountable cloak of dust. You can almost feel a quiet reverence for these tireless explorers as you drift here in the deep quiet. Then, in March 2006, another Guardian arrived, NASA's Mars Reconnaissance Orbiter. You watch, in your mind's eye, as it began the meticulous, now familiar ballet of era-breaking, a 6-month-long dance with the planet's upper atmosphere. This fuel-saving maneuver ensures the craft will continue its vigil above Mars well into the 2030s. One of its crucial roles became that of a celestial switchboard, a communications relay station with a formidable 3-meter antenna capable of transmitting vast amounts of data in the ultra-high frequency band. By November 2013, it had astonishingly tripled the total data sent back to Earth by all previous NASA Mars missions combined. Quite the upgrade, wouldn't you say? Its high-resolution imaging science experiment, HI-RAC, camera began painting breathtakingly detailed portraits of the Martian surface, unveiling active, shifting dunes in East Candor Chasma, polar regions stripped bare of seasonal dry ice, surrounded again by dunes, and intricate pits in the southern hemisphere's residual carbon dioxide cap. The poles of Mars, in particular, began to draw intense interest as Follow the Water became NASA's impassioned rallying cry. This quest led to the Phoenix lander, targeted precisely at the northern polar region, designed to delve deeper into information from Mars' Odyssey, which suggested pockets of frozen water lay just beneath the surface there. Because prior imaging had revealed the region to be remarkably uniform, a rover was deemed unnecessary. This lander embraced a different approach, decelerating with a parachute before using rocket thrusters for a gentle, pinpoint touchdown, eschewing the bouncy airbag method of its predecessors. This decision, however, wasn't without controversy. Some researchers worried the rocket fuel might contaminate the very area Phoenix was meant to meticulously analyze, but nothing to worry about, probably. After a cautious 15-minute wait, allowing any stirred dust to settle, Phoenix gracefully deployed its solar panels. Having landed in the early Martian spring, the northern hemisphere offered abundant sunlight for its planned 90-sol mission, a beacon of hope shining on the icy plains. From our vantage point, perhaps on a gentle cruise through the celestial currents, you can almost feel the whispers of a bygone mission far away on the Martian surface. Picture the Phoenix lander, a silent sentinel equipped with an intricate meteorological station. You might imagine a tiny wind indicator on its mast, softly swaying in the thin atmosphere, its pressure and temperature sensors diligently noting the daily rhythms of an alien world. And then there was its LiDAR, a silent beam reaching up, piercing the ochre haze to catch glimpses of ethereal cirrus clouds or the faint, almost ghostly descent of snow. Phenomena never before witnessed by human eyes, a quiet marvel, wouldn't you say? Its robotic arm, a patient limb of exploration, slowly extended, digging a delicate half-meter into the ruddy soil. We watch as it lifts precious samples, delivering them to a miniature laboratory on board, a clever fusion of high-temperature ovens and a mass spectrometer, ready to unlock Martian secrets. The cameras, ever watchful, once caught sight of a strange white substance in one of its excavations. It lingered for a time, a fleeting ghost, then gradually vanished. The science was clear. Given the temperatures and its brief existence, it could only have been water ice, gently sublimating back into the void once exposed to the sun. The soil, a slightly alkaline blend, also held perchlorate, an unexpected discovery, but not a happy one for those quietly hoping for abundant Martian life, as it tends to be quite inhospitable to microbes. Phoenix, a diligent worker, graced the red planet with its presence for 2 months longer than anticipated, before the encroaching Martian winter, with its long, deep shadows, finally drew a veil over its solar panels, bringing its diligent work to a graceful close. Even with little surface ice remaining, it became undeniably clear that Mars held vast subterranean deposits, an icy heart beating beneath its dusty exterior. We began to understand, with a growing sense of quiet awe, that many of the planet's dramatic features, the vast canyons, the sprawling plains, were not sculpted by wind alone, but had been patiently carved by the flow of ancient running water. Did you know Mars was once covered in rivers and lakes, a world that might have hosted life long before humans even existed? You drift effortlessly through the quiet of your vessel, the faint hum of distant engines, a soft lullaby against the endless dark. Ahead, the red planet glows faintly in starlight, its thin atmosphere barely holding on, its surface cold and silent. And yet, somehow, you can feel traces of the warmth that once was ancient rivers carving paths through dusty plains, a ghost of life that might have been our probes. Those tireless robotic explorers have uncovered layer after layer of Mars' secrets. Each mission teaches us something new, yet Mars always seems to ask more questions than it answers. You find yourself staring out the window, wondering if this quiet, red world really was a home once. imagining the first sparks of life in a place now so still. Think of Giovanni Schiaparelli in 1877, mapping Mars by hand, convinced he saw canals, or Percival Lowell decades later, certain those lines meant intelligent life. Their hope set humanity on a quest that continues even now. By 1962, the Soviets tried to reach Mars with their Mars M1 flyby. It failed, fiery disappointment lost in space. Yet ambition never quit. In 1971, NASA's Mariner 9 finally entered orbit, only to be swallowed by a planet-wide dust storm, its cameras capturing little but swirling red chaos. Soon, Soviet orbiters joined, carrying their own landers, each one silently circling, waiting for Mars to reveal its secrets. And here you are, floating gently past it all, feeling the calm of space that those early pioneers never knew. 1. The Mars 2 lander met a swift and fiery end, crashing into the obscured surface. The Mars 3 lander, however, miraculously made it down intact, only to transmit one garbled, ghostly image before falling silent forever. Now, you had 3 spacecraft patiently circling, all staring at a seemingly featureless, dusty, red sphere. The Soviet probes were programmed for immediate action, but the American Mariner 9 held a crucial difference. NASA could command it to simply wait. Imagine that patience, waiting for months, for the storm to subside, for Mars to reveal itself. And reveal itself it did. Slowly, majestically, the thick atmospheric shroud began to clear, unveiling wonders. Mariner 9's patient gaze was rewarded with the first sight of 3 distinct craters towering above the lingering dust. These were no mere craters, but the majestic summits of giant volcanoes on a region now known as the Tharsis Plateau. Soon, a tapestry of complex geological features emerged from the haze. In some areas, the surface was heavily cratered, a stark reminder that the vigorous tectonic forces that constantly renew Earth's surface were absent here. The colossal volcanic activity, responsible for forging the solar system's largest mountains, had ceased billions of years ago. This patient vigilance allowed scientists to meticulously construct the first accurate global map of Mars, laying the groundwork for future landings, including the Viking probes in 1976. You feel a soft shift in the recycled air, a quiet breath within your ship as you recall the next chapter. The Viking 1 and 2 missions, twin orbiters and landers, gracefully touched down on the Martian surface, returning the very first intimate portraits of the Martian landscape. Their primary directive, the driving pulse of the entire program, was to seek out any telltale signatures of life. But even with their sophisticated instruments, researchers now understand the limitations of those initial experiments. As we on Earth began to explore the tenacious life forms thriving in our own planet's most extreme environments, the question of where life might exist on Mars began to evolve, to deepen. Yet, at that time, the scientific consensus hardened. Mars was sterile. The hopeful whisper of Martian life seemed to die, at least for a while. A long, quiet, 2-decade hiatus followed, a period of introspection and technological evolution. Then, in 1996, a new chapter began as the Mars Global Surveyor gently slipped into orbit. The images it transmitted back were astonishingly clear, far surpassing anything seen before from the red planet. While earlier orbiters had focused on broad mapping, the Global Surveyor delivered high-resolution views that brought ancient Mars vividly to life. You can almost see them now, detailed riverbeds, even the delicate branching patterns of long-dead river deltas etched into the ruddy surface. Yet, the occasional, perfectly formed impact crater scattered across these ancient water systems told a different story. Nothing had flowed here for billions of years, a world preserved in amber, a testament to a long-vanished past. Just a year later, in July of 1997, another intrepid explorer arrived. The Mars Pathfinder was part of a bold new philosophy from NASA's administrator: faster, better, cheaper. The idea was to streamline development, slash budgets, and while acknowledging a higher risk of failure, the reduced cost meant the potential for more missions. Pathfinder's task was to deliver a small rover to the surface, and to do this, it employed a radically new airbag landing technology. Imagine, essentially, a gigantic cosmic bounce house, borrowing safety concepts more from automotive design than traditional spaceflight. The chosen landing site, Ares Vallis, in Mars's northern hemisphere, was notoriously rocky, but thought to be safe enough. It was believed this area held a broad array of rock types, evidence of an ancient, colossal flood. The innovative technique worked flawlessly, a spectacular proof of concept for future missions. The Pathfinder wasn't just a landing craft. It transformed into a sophisticated base station upon arrival. Its 3 solar panels unfolding delicately, like petals unfurling in the alien light. It bristled with sensors, diligently measuring atmospheric pressure, temperature, and wind speed, constantly relaying its findings back to Earth. But its most captivating cargo was the little Sojourner rover, a tiny 6-wheeled explorer that set out to investigate the immediate surroundings. Sojourner, equipped with cameras and an alpha particle X-ray spectrometer, became a global sensation. It was the first mission to have its own dedicated website. It beamed back thousands of images and invaluable data about Mars's atmosphere and geology. Its overwhelming popularity wasn't just a fleeting moment. It guaranteed an exciting future of even more Mars missions. And just like that, Mars was back in vogue, its mysteries once again drawing us in. Then, on a crisp morning, April 7th, 2001, another silent sentinel was launched, the Mars Odyssey orbiter. It carried 3 primary instruments and, crucially, had the ability to serve as a vital relay satellite, a cosmic bridge for all future surface missions to communicate with Earth. Upon its arrival at Mars, it employed a truly ingenious new technique to settle into orbit. After a relatively brief burst from its engines, Mars Odyssey entered a highly elliptical path, its closest approach skimming the planet's incredibly thin upper atmosphere. This brilliant maneuver, known as aerobraking, allowed the craft to slowly, gently circularize its orbit over a period of 3 months, saving a remarkable 200 kilograms of precious fuel. Clever, isn't it? Using the planet itself to slow down, like a whisper in the wind. This quiet, persistent probe is still diligently working today, a testament to ingenuity and endurance, a constant eye watching over our red planet. As the subtle hum of our own vessel softly vibrates through the floor beneath you, echoing the silent dance of distant stars. Imagine the era when Mars truly began to unveil its secrets. For years, Earth kept its gaze fixed on the crimson planet, each mission building upon the last, like layers of stardust settling on a long-lost dream. Then, in December of 2003, a fresh whisper of ambition reached the Red World from the European Space Agency. Gracefully launched by a Russian rocket, came Mars Express, their inaugural planetary explorer. You might feel a gentle pull as your own ship subtly adjusts its orientation, mirroring that distant journey. Mars Express arrived with a companion, a tiny lander known as Beagle 2, though sadly, its voice was lost to the Martian winds. Yet, the main orbiter persevered, a tireless messenger sending back invaluable data, so much so that its mission has been extended repeatedly, its journey stretching beyond expectations. From your console, the soft, ambient glow reflects tiny flecks of cosmic dust dancing in the recycled air as you visualize the stunning 3D panoramas it sent home. Sculpted from its higher resolution stereo camera, its gaze peeled back the planet's icy layers, revealing a curious blend of frozen carbon dioxide and water ice at the poles. Just imagine that, a frozen alien wonderland. But it was in the Martian atmosphere that Mars Express truly startled us, first detecting hints of methane, then ammonia. Both these gases are fleeting, quickly broken down by sunlight, meaning there must be an ongoing source, a continuous whisper of activity on the planet. While they can sometimes be formed inorganically, these molecules are more often linked to life itself. Isn't that just like space? Always offering tantalizing possibilities just beyond reach? You might need a moment to just float here, letting that thought drift through your mind like a wisp of nebulae. Barely a month after Mars Express settled into orbit, a new pair of emissaries from NASA began their descent towards the Red Planet, a duo of identical craft arriving just 3 weeks apart. You feel the gentle sway of our ship, almost as if you're witnessing their delicate ballet from nearby. These were the Mars exploration rovers, affectionately named Spirit and Opportunity. Spirit, the first to touch down, aimed for the expansive Gusev crater, while Opportunity sought out the intriguing Meridiani Planum, a world away on the opposite side of Mars. Though considerably heavier than their Pathfinder predecessor, they embraced the familiar, quirky bounce landing technique, enveloping themselves in protective airbags. Both landings were textbook successes, each craft settling precisely on target. A collective breath was held across the vastness of space. After a moment, as if stretching after a long journey, each craft righted itself, detaching from its protective shell, and began the autonomous, deliberate unfurling of its solar panels and camera mast. Back at the Jet Propulsion Laboratory, on a distant blue marble, the team waited in hushed anticipation for signals. Those vital confirmations that took a nail-biting 15 minutes to traverse the cosmic distance. Many had poured years of their lives into this endeavor, and now the true adventure was finally beginning. You can almost feel the collective relief rippling across the void. These resilient rovers were initially designed for a mere 90 Martian days, or sols, as the science team affectionately called them. Given that a Martian day is just a bit longer than an Earth day, mission designers, acutely aware of Mars' infamous dust storms, fully expected the rover's solar panels to eventually succumb to a layer of grime, silencing them forever. But, Mars had a surprise in store. The planet's capricious winds often swept the panels clean, granting them an unexpected reprieve. Soon, Opportunity, exploring its new home, sent back undeniable proof: stratified rock patterns in Meridiani Planum, hinting at ancient sedimentation, alongside specific distributions of chlorine and bromine that whispered of a past as a salty sea. This was it, confirmation of liquid water. In April 2004, the initial 3-month mission for the rovers was extended to 8, a decision that would become just the first in a long series of improbable extensions, testament to their astonishing tenacity. The very air around you seems to hum with the echoes of their incredible journey. Each rover carried an ingenious abrasion tool designed to gently grind away a rock's surface, exposing pristine layers for analysis. Spirit first deployed this marvel on a rock aptly named Adirondack in Gusev Crater, a pioneering moment in planetary geology. The researchers agonized over using it, knowing the energy it drained from the rover's precious budget, but the payoff was immense. The rock, composed of olivine, pyroxene, and magnetite, bore a striking resemblance to Earth's volcanic basalt. Later, when Spirit's right front wheel seized, engineers devised a clever reversing technique, using a duplicate rover back on Earth, allowing Spirit to drag its inert limb, leaving a furrow in the soil. This unexpected gouge became a new research area, revealing white and yellow deposits within the trench, various salts that form only in the presence of hot water. On Earth, hot water environments often teem with microbial life. Spirit valiantly limped on for another 3 years, a testament to its engineering and determination, before finally becoming hopelessly mired in loose sand. Despite tireless efforts with its replica, nothing could free the intrepid rover. Spirit was ultimately declared a stationary research platform, its solar panels tragically unable to orient for optimal light. The last faint message from Spirit arrived in March 2010. Opportunity, however, continued its odyssey until June 2018, its long journey ending only when its solar panels finally succumbed to an insurmountable cloak of dust. You can almost feel a quiet reverence for these tireless explorers as you drift here in the deep quiet. Then, in March 2006, another Guardian arrived, NASA's Mars Reconnaissance Orbiter. You watch, in your mind's eye, as it began the meticulous, now familiar ballet of era-braking, a 6-month-long dance with the planet's upper atmosphere. This fuel-saving maneuver ensures the craft will continue its vigil above Mars well into the 2030s. One of its crucial roles became that of a celestial switchboard, a communications relay station with a formidable 3-meter antenna capable of transmitting vast amounts of data in the ultra-high frequency band. By November 2013, it had astonishingly tripled the total data sent back to Earth by all previous NASA Mars missions combined. Quite the upgrade, wouldn't you say? Its high-resolution imaging science experiment, HI-RAC, camera began painting breathtakingly detailed portraits of the Martian surface, unveiling active, shifting dunes in East Candor Chasma, polar regions stripped bare of seasonal dry ice, surrounded again by dunes, and intricate pits in the southern hemisphere's residual carbon dioxide cap. The poles of Mars, in particular, began to draw intense interest, as Follow the Water became NASA's impassioned rallying cry. This quest led to the Phoenix lander, targeted precisely at the northern polar region, designed to delve deeper into information from Mars' Odyssey, which suggested pockets of frozen water lay just beneath the surface there. Because prior imaging had revealed the region to be remarkably uniform, a rover was deemed unnecessary. This lander embraced a different approach, decelerating with a parachute before using rocket thrusters for a gentle, pinpoint touchdown, eschewing the bouncy airbag method of its predecessors. This decision, however, wasn't without controversy. Some researchers worried the rocket fuel might contaminate the very area Phoenix was meant to meticulously analyze, but nothing to worry about, probably. After a cautious 15-minute wait, allowing any stirred dust to settle, Phoenix gracefully deployed its solar panels. Having landed in the early Martian spring, the northern hemisphere offered abundant sunlight for its planned 90-sol mission, a beacon of hope shining on the icy plains. From our vantage point, perhaps on a gentle cruise through the celestial currents, you can almost feel the whispers of a bygone mission far away on the Martian surface. Picture the Phoenix lander, a silent sentinel equipped with an intricate meteorological station. You might imagine a tiny wind indicator on its mast, softly swaying in the thin atmosphere, its pressure and temperature sensors diligently noting the daily rhythms of an alien world. And then there was its LiDAR, a silent beam reaching up, piercing the ochre haze to catch glimpses of ethereal cirrus clouds or the faint, almost ghostly descent of snow. Phenomena never before witnessed by human eyes. A quiet marvel, wouldn't you say? Its robotic arm, a patient limb of exploration, slowly extended, digging a delicate half-meter into the ruddy soil. We watch as it lifts precious samples, delivering them to a miniature laboratory on board, a clever fusion of high-temperature ovens and a mass spectrometer, ready to unlock Martian secrets. The cameras, ever watchful, once caught sight of a strange white substance in one of its excavations. It lingered for a time, a fleeting ghost, then gradually vanished. The science was clear. Given the temperatures and its brief existence, it could only have been water ice, gently sublimating back into the void once exposed to the sun. The soil, a slightly alkaline blend, also held perchlorate, an unexpected discovery, but not a happy one for those quietly hoping for abundant Martian life, as it tends to be quite inhospitable to microbes. Phoenix, a diligent worker, graced the red planet with its presence for 2 months longer than anticipated, before the encroaching Martian winter, with its long, deep shadows, finally drew a veil over its solar panels, bringing its diligent work to a graceful close. Even with little surface ice remaining, it became undeniably clear that Mars held vast subterranean deposits, an icy heart beating beneath its dusty exterior. We began to understand, with a growing sense of quiet awe, that many of the planet's dramatic features, the vast canyons, the sprawling plains, were not sculpted by wind alone, but had been patiently carved by the flow of ancient running water. Samples meticulously analyzed from across the globe affirmed this truth. Water, and nothing else, was the primary architect of the Martian landscape. Isn't that just like space, always revealing its secrets in fragments? Mars, it seemed, had once been a warmer, wetter world, far more akin to our own blue marble. But it had somehow shed its surface water and most of its protective atmosphere, leaving us with a profound, persistent question. Could life have truly emerged in that ancient, more hospitable past? And, even more tantalizingly, could it still be present, hidden away in the dark, cold depths below its current, desolate surface? The universe, as always, demanded answers. And so the next great Martian mission was conceived. It was NASA's most ambitious endeavor yet, a car-sized rover affectionately named Curiosity. This new explorer would be powered by a nuclear battery, a robust heart ensuring its resilience against the pervasive dust storms that had plagued its predecessors, Spirit and Opportunity. We picture its launch in November 2011, a fiery arc against the Earth's night sky from Cape Canaveral, atop an Atlas V rocket, the countdown echoing in a distant memory. 7, 6, Curiosity, main engine start, 0, and liftoff. Then came the long, silent journey through the void. In mid-2012, after months of patient travel, it finally kissed the Martian atmosphere, a fiery streak heading for the colossal expanse of Gale Crater. The Jet Propulsion Laboratory monitored its approach with bated breath, their sophisticated instruments relaying data across millions of miles, yet utterly powerless to intervene in the delicate dance of entry through Mars's thin, unforgiving atmosphere. The parachute, a vast, elegant bloom, could only slow the heavy craft to a still terrifying 320 kilometers per hour. A fleeting thought, imagine being there, the immense friction, the silent descent. As it hurtled closer to the ruddy surface, the descent stage dramatically detached from its protective aeroshell, and powerful retrorockets ignited, a controlled burn fighting against the planet's gravity. Radar beams, silent and precise, painted an intricate map of the terrain below, guiding the heavy lander with incredible accuracy. A small camera, quietly worried, began to record the first intimate glimpses of the Martian landscape rushing up to meet it. Then came the ingenious sky crane maneuver, a feat of engineering ballet. Curiosity, suspended on a tether beneath the descent stage, was gently lowered, a delicate spider on an invisible thread. This brilliant technique minimized the dust stirred up by the rockets, protecting the fragile rover from unnecessary contamination and harm. Everything unfolded with breathtaking precision, a perfect pirouette. You can almost feel the collective sigh of relief from the engineers back on Earth, a quiet wave of triumph washing over the control rooms. It was, without a doubt, the most precise landing ever achieved on another world, a moment of profound success. The soft vibration from our own ship's hull seems to echo that distant, perfect touchdown, once safely on the ground, before commencing its grand adventure. Curiosity's internal computers diligently cycled through an extensive checklist, a silent assurance that every system was perfectly aligned and ready for its monumental task. It was a full day of quiet preparation before its camera mast and communication antennas, like a newly awakened creature, slowly unfurled and reached towards the Martian sky. Gale Crater itself, an ancient basin, is thought to be a staggering 3.5 billion years old. Its towering central mound, a testament to epochs of geological activity. Its layered sediments tell a profound story, first laid down by the patient work of water, then gently refined over eons by persistent winds. What a canvas for discovery. Now, NASA has a truly sophisticated mobile science laboratory diligently exploring this ancient landscape, connected to us on Earth by the most advanced communication links, all thanks to the ever-watchful Mars Reconnaissance Orbiter. Curiosity's primary objective, its very reason for being, is to seek out the elusive truth. Did conditions suitable for life ever exist on Mars? Or, perhaps, do they still persist in some hidden corner? It also tirelessly gathers crucial data on the planet's current, often harsh, environmental conditions, especially the levels of radiation which will undoubtedly impact any future manned missions. A subtle shift in the cabin temperature reminds you of the vast emptiness surrounding us and the immense challenges these missions face. Curiosity, a tireless geological detective, has already analyzed dust samples from countless holes it meticulously drilled, revealing a suite of elements that resonate with our understanding of life: sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all the essential building blocks, right there on Mars. In its 6 years of quiet exploration on the surface, this tenacious rover has trundled some 20 kilometers, a patient, slow journey across a vast, ancient stage. But the relentless driving, the grinding of alien terrain, is taking its toll. It routinely sends back a series of self-portraits, almost as if checking its own pulse, mainly for diagnostic reasons. Its wheels, a testament to the harsh environment, have suffered severe damage, an experience that will undoubtedly lead to design changes for the next generation of Martian explorers. Its computers, too, are beginning to show the strain of years of service, reminding us that even the most advanced machines have a lifespan. But don't worry, the spirit of exploration never wanes. A new suite of missions is slated to arrive at Mars in the 2020s, ready to continue profiling this enigmatic world. Yet, amidst all this surface exploration, one profound aspect of the Martian environment has always remained a mystery, untouched and uninvestigated until now. The Mars Insight probe, a specialized listener, was precisely targeted at the flat, expansive Elysium Planitia, conveniently close to the Martian equator. Its 2-year mission to delve deep into the planet's very interior. It made a flawless landing in November 2018, a quiet, perfect touchdown. After gracefully unfurling its solar arrays like opening delicate wings, it patiently spent weeks selecting the ideal spot to deploy its seismometer directly onto the Martian surface. Imagine this sophisticated instrument now quietly monitors Marsquakes, listening to the subtle tremors and rumblings from within the planet. While it's clear Mars once enjoyed a warm, wet past, it's now a cold, very dry world. By understanding its deep geological activity, InSight aims to help us uncover why Mars changed so dramatically. The probe also painstakingly hammered a thermal sensor into the surface, a delicate probe gathering data on the heat flowing from the planet's core. By understanding these inner processes, we can begin to unravel the cosmic tale of how the geological histories of Mars and Earth began to diverge, becoming the distinct worlds we know today. You might need a moment to just float here, pondering the sheer scale of planetary evolution. Now, as our journey continues, let's allow our gaze to drift far beyond the familiar red glow of Mars, further into the cosmic ocean, to an entirely different kind of world. Here, almost 100 times the mass of Earth, lies the majestic, ringed planet, Saturn. It's a true gas giant, a colossal sphere where a dense metallic core resides beneath a staggering 80,000 kilometers of swirling liquid hydrogen and helium. The sheer scale is almost incomprehensible, isn't it? Saturn is attended by a celestial court of at least 62 moons, each one a unique world unto itself, some boasting incredibly complex and dynamic environments, miniature universes orbiting a giant. Our only truly detailed examination of this magnificent Saturnian system came to a poignant end in 2017, when the Cassini probe, a faithful explorer for over a decade, was intentionally guided into the planet's dense, swirling atmosphere. This deliberate act, a final, selfless sacrifice, was made to guard against any accidental contamination of those pristine, unique moons, a remarkable testament to our commitment to protecting potentially delicate alien ecosystems. You can almost feel the gentle hum of our ship's engines, a steady thrum in the boundless quiet of space. As Saturn's distant, ethereal rings begin to fill our viewport, from Earth, Saturn's iconic rings are undeniably visible, a breathtaking spectacle, yet without any real detail. For a long time, early observers believed them to be solid disks, perhaps remnants of a shattered moon. But then, mathematical analysis, a triumph of human intellect, suggested a far more intricate truth. They were, in fact, composed of countless orbiting particles, billions upon billions of icy fragments. This naturally begged the most profound questions. How did they get there? And why was Saturn alone in possessing such a magnificent, shimmering crown? In the early nascent days of space research, Saturn seemed impossibly distant, an unreachable jewel. Conventional rockets of the era could barely manage the journey to Mars, let alone the colossal distances to the outer solar system. But then, in 1964, a stroke of cosmic luck was recognized. NASA scientists realized that a probe launched in 1977 could cleverly harness the gravitational pull of a rare planetary alignment, using it like a celestial slingshot to propel it across the vast void. Isn't that just like space? Sometimes offering a helping hand, if only you know how to ask. The starlight reflects softly off your console, a quiet dance of light in the recycled air of our craft, as we continue our patient drift through the awe-inspiring depths of the universe. Imagine a time not so long ago when the vast, uncharted expanse of our solar system still held its deepest secrets, particularly beyond the orbit of Mars. Whispers circulated among the quiet hum of advanced control rooms, murmuring of a daring concept. What if we could journey to the most distant gas giants simply by letting the celestial ballet of gravity pull us along? It was a grand dream, almost fantastical, to harness the very planets themselves, slingshotting a craft from one to the next, a monumental grand tour taking shape in the minds of the intrepid. You might feel a gentle pull now, a subtle shift in your own ship's gravity, mimicking that grand theoretical embrace. Before embarking on such an ambitious voyage with the sophisticated Mariner series, later known as Voyager, prudence dictated a cautious approach. No human-made object had ever ventured beyond Mars, leaving the deep space environment a colossal unknown. Could a craft even survive the perilous asteroid belt, that swirling river of cosmic debris between Mars and Jupiter? To answer these crucial questions, a pair of more rudimentary scouts, Pioneer 10 and 11, were dispatched. You can almost hear the faint, hopeful thrum of their engines from across the light years, a quiet bravery echoing through the void as Pioneer 10 launched towards Jupiter in 1972, followed by its twin, Pioneer 11, a year later, aiming for Saturn. What a journey to undertake, isn't it? As these plucky pioneers navigated the cosmic currents, they uncovered a startling truth at Jupiter. The electron radiation surrounding the gas giant was a staggering 10,000 times more intense than anything experienced back on Earth. Quite the jolt. You might think, feeling a slight chill ripple through the recycled air of your cockpit, a reminder of the universe's unpredictable temperament. This unexpected discovery sent a quiet flurry of activity through the engineering labs at NASA, requiring careful modifications to the more complex craft to a prand to tour or a twin tour, but of tour of twin Kurav so of poo with pew of you would to I go will kaya I dip to you I type to at you I've up to you I got I you you baba mark I hope I'm crazy I do if I were to do you but what I've my papa did that happened you I will face These magnificent probes, initially conceived as part of the Mariner Jupiter-Saturn program, quickly adopted a new, more fitting moniker, the Voyager program. Then, in late 1977, separated by a mere 16 days, they launched, embarking on a journey that would redefine our understanding of the cosmos. While Pioneer 10 continued its lonely trajectory towards the interstellar void. Pioneer 11, in 1979, was still 2 years from its ultimate destination, Saturn. Yet, as it drew closer, it began to transmit images of the ringed jewel, far clearer than anything ever witnessed. You can almost feel the anticipation, the gentle vibration through your ship's hull, mirroring the excitement of that moment. A new ethereal band, the F-ring, was observed for the very first time. The craft then made a daring pass, flying directly beneath the rings. There was genuine uncertainty about the density and spread of those icy particles, a palpable risk. Mission planners, in a testament to pure scientific dedication, were prepared to sacrifice Pioneer 11 to pave a safer path for the following Voyager craft. Fortunately, it passed through unscathed, a cosmic pathfinder continuing its silent drift into the profound interstellar darkness. NASA's final whisper from it faded on November 24, 1995. The Voyager 1 and 2 probes, on the other hand, were built with an extraordinary resilience, crafted to endure an incredibly long journey, carrying far greater technical prowess than their pioneer predecessors. In late 1980, Voyager 1 finally approached Saturn. Despite a minor setback, its higher-resolution polarimeter quietly failed. It still unveiled another new ring, the G ring, a delicate band orbiting 100,000 kilometers above Saturn's swirling cloud tops. You can almost imagine the faint console lights around you dimming and brightening with each incoming data packet, a ballet of information. For the first time, researchers could observe the subtle, elegant dance of the rings, noticing uneven features. Transient spokes believed to be particles lifted by an electrostatic charge. After years of meticulous preparation, data flooded into JPL, a torrent of cosmic revelation that quite literally overwhelmed the planetary scientists. It truly was a moment of profound discovery, wasn't it? Saturn's many moons also held immense interest, particularly Titan, the solar system's second-largest moon and the only one known to possess a substantial atmosphere. Voyager 1's trajectory had been specifically chosen to provide a close encounter with this enigmatic world. Yet, as the images began to filter back, a quiet disappointment settled. The thick, orange-hued veil of methane and nitrogen proved impenetrable, cloaking Titan's surface in mystery. You might feel a gentle sigh escape you, understanding that veiled frustration. With its primary objectives at Saturn complete, Voyager 1 performed a graceful loop up and away, arcing above the solar system, setting a course for the endless expanse of interstellar space. As it looked back, it captured one last, breathtaking image of Saturn from a unique, poignant angle, a final farewell before its long, quiet journey. It was nearly 10 months later when Voyager 2 finally neared Saturn. Its meticulously planned, different path, a subtle curve in the fabric of space, meant it could continue its grand expedition onward to Uranus and then, ultimately, to Neptune. Its high-definition camera, thankfully, was still functioning flawlessly, and planetary researchers eagerly anticipated detailed, high-resolution pictures of the magnificent rings. They were not disappointed. The varying densities and intricate spacing within the rings revealed a complexity far beyond anyone's wildest expectations. You might need a moment to just float here, letting your gaze trace the impossible beauty of such cosmic artistry. Though the rings stretch from 7,000 to 80,000 kilometers above Saturn's equator, their average thickness is astonishingly just 30 meters. The spacecraft also returned captivating images of the moon Enceladus, revealing a cracked, surprisingly uncratered surface of pure ice, beneath which, tantalizingly, lay a subsurface ocean. What secrets might still be hidden there, simply waiting? Ultimately, Voyager 2 left Saturn, unable to enter orbit, speeding onward towards the distant, sapphire gleam of Uranus, a true cosmic trailblazer. Indeed, it would be 23 years before another probe visited Saturn. That next great odyssey began with the liftoff of the Cassini spacecraft in 1997, a monumental collaboration between NASA, the European Space Agency, and the Italian Space Agency. It would embark on a deliberate, unhurried voyage, taking more than 6 years to finally reach the ringed planet. Cassini wasn't just a probe, it was a leviathan of exploration, the biggest, most complex interplanetary spacecraft ever conceived at that time. You can almost feel the sheer weight of its ambition, the subtle hum of its intricate systems working in unison. It carried 12 distinct instruments, each with its own dedicated team of research specialists back on Earth, meticulously waiting to decipher the secrets it would transmit. Its magnificent high-gain antenna, a shimmering parabolic dish reflecting distant starlight, served as its primary conduit for high-speed data relay back to Earth. But in a clever, tactical ram maneuver, it could also be angled and used as a robust shield, protecting the precious spacecraft from potential debris impacts, particularly during its daring crossings through the plane of Saturn's rings. Then, on a fateful day, July 1st, 2004, Cassini fired its main engine, a long, controlled burn designed to ease it gently into orbit around Saturn. This vessel was engineered with redundancy in mind, a true testament to foresight. Beside its primary engine, a backup stood ready, just in case. It even possessed 16 monopropellant thrusters, 8 prime and 8 more as backups, a cosmic Swiss Army knife of propulsion. Why does the universe always demand such meticulous planning? In the quiet control rooms of the Jet Propulsion Laboratory, engineers could only wait, watching the recorded telemetry. The immense time delay, combined with Cassini's temporary disappearance behind the colossal body of Saturn, meant that much of the engine burn data was recorded for later replay back on Earth. The main engine fired for a breathtaking 106 minutes, a symphony of controlled power. Cassini was also a pioneer in its own right, the first probe to employ a solid-state recorder, a vast improvement over the mechanical tape recorders of its Voyager predecessors. Its very first orbit around Saturn traced a highly elliptical path, specifically designed to swing it out past the Moon Titan. This maneuver was crucial for 2 reasons. Titan's immense gravity would provide a vital assist, subtly modifying Cassini's course, allowing for diverse observation angles of Saturn and its other moons. And secondly, Titan itself, with its mysterious, dense atmosphere, remained a primary target of profound scientific interest for the Cassini team, a veiled world waiting to be uncovered. You might even recall the European Space Agency had built a small craft named Huygens specifically for this purpose. You watched as a tiny seed of exploration, the Huygens probe, gently detached from Cassini, beginning its solo journey towards the veiled moon of Titan. A soft glow from your console lights flickered, casting long shadows across the cabin as the separation sequence completed, accompanied by the low, steady hum of your ship's engines. This small Voyager, equipped with its robust heat shield and a delicate parachute, carried enough power for several weeks, ready to send back whispers from a distant world. For 20 long days, Huygens drifted, covering an incredible 4 million kilometers, a silent ballet across the inky blackness meticulously transmitting its observations back to its parent craft, which in turn would relay them back to Earth. Just a few days after that quiet separation, you might have felt a subtle, almost imperceptible shift in your own ship's trajectory, a gentle reorientation as Cassini made a crucial course correction. This slight maneuver was designed to prevent any accidental collision with Titan, ensuring that as Huygens began its final descent into the moon's thick atmosphere, Cassini would be perfectly positioned, circling around for its third close pass. It waited, a patient sentinel, ready to catch the precious signals from the intrepid lander, its instruments poised, anticipating the first breath of data from a world only imagined. As Huygens plunged through Titan's hazy atmosphere, you saw the data unfold on your main screen, revealing an alien landscape beneath the perpetual clouds. The first images, grainy at first, then sharpening, unveiled a world of low, rounded hills and intricate channels, undeniably carved by flowing liquid, though not water as you know it. There were few impact craters, and those visible appeared softened, heavily eroded, as if time and an unknown weather had gently smoothed them away. This was a truly monumental moment, wasn't it? The very first landing on a body so far out in our solar system. The pictures relayed from the surface showed rocks, surprisingly weathered, but clearly composed of water ice. Yet, the real revelation, the one that truly surprised everyone, was the discovery that Titan is a geologically active world. Here, liquid, ethane, and methane, not water, were the sculptors of its dramatic features. You continued to observe as Cassini, looping gracefully around Titan, employed its radar to map the moon's enigmatic surface, confirming vast, shimmering distributions of hydrocarbon lakes. And then, the incredible news: rain falls on Titan, a strange, ethereal mix of liquid, ethane, and methane. Imagine that, a moon with its own weather, its own erosive forces, strikingly similar to Earth's, yet with a chemistry utterly, wonderfully different. A fascinating place, indeed. Then, your attention was drawn to another small moon, Enceladus, a celestial pearl, gleaming as the whitest, most reflective body you've ever seen in the solar system. Its northern hemisphere bears the familiar marks of impacts, but its southern pole is a spectacle of giant, enigmatic cracks, dramatically nicknamed tiger stripes. On Cassini's very first pass, the magnetometer team noticed an unusual deflection in Saturn's magnetic field, a tiny anomaly, as if this small, icy moon possessed an atmosphere. The universe always has its little secrets, doesn't it? During its second flyby, the same phenomenon reappeared, sparking a quiet, persistent curiosity. The team, ever so gently, requested an even closer approach for the next traverse. And so, Cassini's course was subtly modified, charting a path that would bring it to a mere 175 kilometers above the icy moon's surface. You could almost feel the anticipation building, a silent hum through the hull of your own ship, as the probe prepared for its daring dive. It was a risky move, but one that promised untold discoveries. And so Cassini made its perilous journey, passing directly through a plume of water vapor, majestically erupting from those very tiger stripes. Imagine that, a fountain of ice and gas in the vacuum of space, containing something so familiar as common salt. Cassini, in its tireless dedication, completed no less than 24 swoops past Enceladus, with its closest approach taking it a breathtaking 25 kilometers above the surface. Each instrument on board became an eager detective, gathering distinct evidence about these incredible jets of water continuously expelled through the cracks in the moon's southern pole. A marvel of nature, wouldn't you agree? While rovers on Mars tirelessly comb the dusty surface, seeking the faintest whisper of past life, Enceladus, in its quiet brilliance, was practically flaunting remarkable signs. Gravitational analysis revealed a vast liquid ocean, hidden deep beneath its icy shell, while infrared detectors confirmed heat radiating from those distinctive cracks. Beyond the familiar salt, the science team unearthed traces of silica, a compound that astonishingly can only dissolve in hot water. And there was more. Hydrogen and organic compounds were also detected. It's like finding pieces of a cosmic puzzle scattered across the void, now slowly fitting together. From Cassini, we now definitively know Enceladus harbors a global ocean, so liquid water, check. And those organics, directly measured in both gas and particles, swirling in the plumes, another check. We also know there's a source of energy. The South Pole was noticeably warmer than the rest of this little moon. Then came the most exciting piece, evidence of hydrothermal vents deep on Enceladus's seafloor. These are the very vents that could supply the heat and the nutrients, the very lifeblood that might sustain life. But with a mere 500-kilometer diameter, Enceladus is just too small to keep a core hot through radioactive decay alone. Saturn's gravitational squeezing explains some of the warmth, but the precise source of those intense temperatures remains, for now, a beautiful mystery. So, you see, it's not just liquid water hiding beneath that icy surface. There's organic material, and there's a consistent heat source. When we get truly excited about the potential for life elsewhere in our solar system, we generally look for 4 key ingredients: a heat source, liquid water, organic material, and the stability of those 3 over time for life to potentially form. On Enceladus, we've found 3. The stability over time is the final, compelling question mark, isn't it? It leaves a gentle space for wonder, doesn't it? Here on Earth, deep within our own oceans, hydrothermal vents provide the warmth and vital nutrition that support a riot of life. Some even believe they played a crucial role in the very origins of life itself. Planetary biologists now quietly speculate that the environment within Enceladus's hidden oceans might just be the most promising place in our solar system to encounter some form of extraterrestrial life. You might need a moment to just float here, suspended in the quiet hum of your own ship, letting that profound possibility settle in the vastness of your thoughts. It required some patient positioning, a clever cosmic ballet, for Cassini to align itself perfectly so that the sun's backlighting could illuminate the elusive plumes for the imaging team. Using a similar ingenious technique, they captured a breathtaking picture with Saturn positioned directly between Cassini and the sun. This revealed Saturn's earring, that incredibly hazy outermost ring, usually so difficult to discern against the void. This ethereal ring, you see, is a direct result of the continuous plumes from Enceladus, constantly replenished by those saline eruptions. Isn't that just like space, always connecting things in the most unexpected ways? To simply say Saturn has 62 moons is, frankly, a little misleading. Any particle within its magnificent ring system could, in truth, be considered a moon. There are the familiar inner large moons and the mysterious outer ones. There are the shepherds that gracefully sculpt the rings, the corbitants that playfully exchange orbits, and even moons that orbit other moons, each one a unique, silent dancer in this grand cosmic performance. During the earlier Voyager missions, the moons were almost an afterthought, a bonus discovery. But for Cassini, a close examination of these fascinating worlds was meticulously planned from the very beginning. Now, let's turn our gaze to Iapetus, a moon that orbits Saturn far beyond Titan. It was first glimpsed way back in 1671 by Giovanni Cassini himself. He could clearly see it as a bright dot of light when it was to the west of Saturn. But then, mysteriously, it would vanish when it should have appeared to the east. A cosmic riddle, centuries in the making, wouldn't you say? What could possibly cause such a strange disappearance? Iapetus, you see, has one strikingly bright face and one utterly dark one. This is because the moon is tidally locked to Saturn, meaning the same dark face always leads as it orbits. One theory suggests it's constantly sweeping up dark, reddish debris spewed from Phoebe, a more distant, enigmatic moon. But then, there's another feature that has scientists truly baffled: a colossal ridge that stretches along its equator for more than halfway around the moon, an immense, mountain-like wall that stands twice as tall. We've been drifting through this cosmic sea, and as your gaze falls upon Iapetus, nestled in the vastness, you can almost trace the mighty ridge that girdles it, making this moon, though a mere 1,500 kilometers across, appear uncannily like a giant walnut suspended in the void. Imagine a mountain higher than any on Earth, encircling an entire world. It's a testament to the strange artistry of the universe, isn't it? Our own vessel's gentle hum is a quiet counterpoint to the silent grandeur around us. The console lights casting a soft glow across the cabin as we observe this celestial marvel. This same cosmic ballet once guided the Cassini probe, a distant echo of our own journey. Mission engineers, with an almost impossible precision, used short, powerful bursts from its main engine to sculpt its looping paths, allowing specialists to linger on Saturn's many moons, especially Titan, a gravity assist that stretched its precious fuel reserves. You might feel a subtle vibration through the hull, a ghost of those long-ago maneuvers. Cassini, a true workhorse, defied expectations, earning 2 mission extensions. But even in the boundless expanse of space, fuel is a finite resource. The planners knew the end was coming, and they saved the most audacious, most hazardous phase for Cassini's final year around the ringed giant. It was late 2016 when the probe began a series of polar orbits, bringing it tantalizingly close to the outer edges of Saturn's magnificent rings, a daring maneuver aptly named grazing on the rings. You can almost picture it, can't you? A cosmic ballet of ultimate risk and reward. The ship's mass spectrometer and cosmic dust analyzer, working in tandem, were poised to scoop up particles and gases as it sliced through the ring plane, gathering invaluable secrets. During orbit 251, its very first pass high above Saturn's North Pole, Cassini recorded a phenomenon that still stirs quiet awe: the peculiar hexagonal storm, a feature barely hinted at by earlier Voyager missions. This colossal tempest, more than twice the diameter of Earth, steadfastly maintains its 6-sided geometry, its color subtly shifting with the advance of Saturn's seasons. At its very heart, a furious cyclone spins, visualized in false colors, where reds mark the lower, warmer clouds, and greens indicate the higher, cooler reaches. The winds at its edges, imagine this, howl at an astonishing 540 kilometers per hour, a swirling masterpiece, really. Sometimes, even the most advanced technology has its quirks. Early in its journey, one part of Cassini's dual-technique magnetometer had failed, meaning the craft had to perform regular, delicate roll maneuvers to keep the remaining instrument calibrated. You might feel a fleeting, almost imperceptible shift in gravity within our own ship, as if we're silently acknowledging the probe's ancient struggle. Each of those 20 ring-grazing orbits was meticulously planned, every instrument's operation mapped out to the second, leaving nothing to chance. What a dedication to discovery! As the sun settled almost directly behind the shimmering rings, Cassini peered into the darkness, searching for telltale dust clouds. Something out there was steadily grinding those majestic ring particles down to a fine, almost ethereal powder, a quiet mystery of the cosmos. The probe also conducted numerous radio occultation observations, using the rings themselves as a cosmic screen between the spacecraft and Earth. 3 distinct radio signals, each with its own wavelength, were broadcast simultaneously, allowing the clever radio science team to meticulously construct a detailed profile of the ring particles. It's like peeling back layers, isn't it? This particular false color image of the O-ring, the outermost of Saturn's bright, expansive bands, beautifully illustrates their findings. Swaths of red denote particles larger than 5 centimeters across, greens highlight those smaller than 5, and blues pinpoint the tiny specks less than a centimeter in diameter. The universe is incredibly intricate. These complex gravitational dance steps between Saturn, its rings, and its moons sculpt the very fabric of the ring system, carving out precise gaps in very particular places. Before Cassini's arrival, only 18 moons were known. Now we marvel at 62, a testament to its tireless exploration. You see how these celestial bodies interact, how they shape each other. Take Prometheus, for instance. It acts as a diligent shepherding moon, gently nudging and confining the inner edge of Saturn's delicate F-ring. And orbiting just outside that same ring is Pandora, its silent partner. Together, these 2 celestial custodians ensure the F-ring remains narrowly confined, a slender, elegant ribbon of ice and dust. It's a delicate balance, a constant negotiation in the silent theater of space. The recycled air within our ship feels almost still, as if holding its breath in admiration. Then came April 2017, marking a pivotal shift in Cassini's journey, the beginning of its final, daring act. The probe's orbit was deliberately altered for the mission's ultimate phase. It would now loop asterisk inside asterisk the magnificent rings, plunging into a territory no craft had ever dared to explore. While this brave maneuver was destined to culminate in its fiery immolation within Saturn's churning atmosphere, the data it would gather from such unprecedented proximity would offer an absolutely unparalleled view of the gas giant, completing its grand portrait. You might feel a slight, almost imperceptible shift in the cabin's temperature, as if sensing the distant heat of that impending, valiant sacrifice. The decision was clear, a poignant choice in the annals of space exploration. Intentionally destroying Cassini was deemed far preferable to allowing it to simply drift, a derelict, fuel-depleted ghost, potentially contaminating one of Saturn's pristine moons. A respectful end, wouldn't you agree? As Cassini began its perilous inner passes, its sensitive instruments started picking up an astonishing phenomenon, a continuous, ethereal shower of ring particles raining down upon Saturn. A steady stream of ice and dust, either dragged toward the planet's equator by its immense gravity, or, at higher latitudes, charged particles spiraling inward along powerful magnetic field lines. Imagine that, a constant, celestial downpour. Every single second, a staggering 10,000 kilograms of this rain falls to Saturn's surface. At this astonishing rate, researchers estimate the rings, those iconic jewels of the solar system, will be completely gone in a mere 100 million years, a geological blink of an eye. Cassini's close passes also yielded another remarkable discovery, catching scientists by surprise: an electric current flowing invisibly, connecting the inner Deering to Saturn's upper atmosphere. The universe always has more secrets to reveal, doesn't it? Towards the very end of Cassini's extraordinary life, as it began to brush against the upper reaches of Saturn's atmosphere, all previously recorded information had been carefully retrieved. Now, data was no longer stored, but streamed directly back to Earth, a real-time cascade of final insights. Yet, this continuous broadcast hinged precariously on the spacecraft's thrusters, firing constantly to prevent it from tumbling, ensuring its high-gain antenna remained precisely pointed. Cassini's very last tasks involved sampling that wispy upper atmosphere and meticulously measuring the subtle offset of Saturn's immense magnetic axis, a magnificent final act of cosmic curiosity. In mission control, a profound stillness settled. Control, in the traditional sense, had vanished. The engineers, thousands of light-minutes away, could now only helplessly monitor the dwindling signals, mere echoes of a spacecraft that had ceased to exist 84 minutes prior. In a cosmic blink, within 45 seconds of the final data packets, the spacecraft itself would be gone, consumed by the very giant it had spent 2 decades studying. It will take countless years to fully unravel the vast tapestry of data Cassini bequeathed us, a legacy for generations. Yet, for now, no future missions to Saturn are etched onto the cosmic calendar. But the universe, dear listener, never stops moving, and neither do we. As we gently pivot our gaze, your ship's thrusters, making a barely perceptible adjustment. A new Titan rises into view, bathing the distant void in its majestic glow. Jupiter, the undisputed monarch of our solar system. It is a world of unimaginable scale, more than twice the mass of all other planets combined, a gravitational behemoth. You, might feel the very slightest pull, a subtle shifting of weight, as its immense presence asserts itself even from afar. Its swirling, banded atmosphere, a kaleidoscope of ochre, cream, and russet, moves with furious independence at different latitudes. And then there's the great red spot, a vast, perpetual storm, churning relentlessly for centuries, a crimson eye staring out into the cosmos. You've heard of it, of course. But even after all we've learned, Jupiter still holds surprises. Recent images from a new probe, daring enough to fly directly above its colossal poles, have unveiled an entirely different, previously unseen aspect of this magnificent planet. A fresh perspective, a new layer to an old story. The ancient Romans, with their profound connection to the heavens, envisioned Jupiter as nothing less than the celestial embodiment of the king of the gods, ruling the sky with undisputed might. A fitting title, wouldn't you say? Then, in 1610, a curious human named Galileo, peering through his newly refined telescope, made a revolutionary discovery. He observed Jupiter's own entourage of moons, clearly orbiting not Earth. This was compelling evidence, quiet but undeniable, that not every celestial body revolved around our world, directly challenging the prevailing wisdom of his time. The soft reflections of distant starlight on our console panels shimmer as you ponder that turning point. Though subsequent improvements in telescopic technology steadily enhanced our understanding of Jupiter, it wasn't until 1964 that a pivotal insight emerged. Gary Flandreau, a brilliant graduate student working part-time at NASA's Jet Propulsion Laboratory, saw what others hadn't. By meticulously plotting the orbital mechanics of the outer planets, he grasped a profound truth. A rare and fleeting planetary alignment would occur in 1977, offering an unprecedented opportunity for a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune, a cosmic slingshot, if you will. NASA, ever eager to seize such a unique chance, swiftly initiated work on twin craft for what became known as the Planetary Grand Tour. But before sending those valuable missions, they needed to scout ahead to minimize any unforeseen dangers. So, two simpler, hardy spacecraft, christened Pioneer 10 and 11, were hastily constructed as cosmic pathfinders. In March 1972, Pioneer 10 made history, becoming the very first spacecraft to successfully navigate the treacherous asteroid belt separating Mars and Jupiter, a truly daunting feat. And because it was the trailblazing probe destined to eventually depart our solar system entirely, it carried a special message, a small golden plaque, a silent greeting to any intelligence that might one day find it. Your ship's faint engine hum seems to resonate with the echoes of those early journeys. A quiet reminder of humanity's boundless curiosity. These pioneers, these brave little vessels, were the vanguard, sending back crucial information about the unforgiving environment around Jupiter, preparing the way for the grander missions that would follow. They truly paved the way for us all. And as you drift, a quiet hum from your ship's core systems, a constant, gentle companion, you recall the early whispers from a pioneering craft. Imagine it, back in December of 1973, a tiny human-made beacon named Pioneer 10 began to beam back visions of Jupiter. The images arriving on distant screens were unlike anything ever glimpsed before, vibrant, detailed, pulling back the veil on a truly colossal world. Yet, as it drew closer, the probe plunged into an environment where unseen forces raged, encountering levels of radiation a staggering 10,000 times more potent than those shielding our own familiar Earth. It's enough to make you shiver, isn't it? Thinking of those invisible hazards just out there in the void. This plucky little craft, as it gracefully skimmed past the gas giant, wasn't just surviving, it was accelerating, picking up phenomenal speed. Leaving Earth, Pioneer 10 had been moving at a respectable 51,000 kilometers per hour, but by the time it departed Jupiter's immense embrace, that velocity had more than doubled. This incredible boost, a cosmic kick, was courtesy of what we call a gravitational slingshot, a celestial ballet where a planet's immense pull can be harnessed to propel a spacecraft further and faster. It was this very principle that would make the ambitious Grand Tour possible for the next generation of explorers, though not without its own set of challenges. The craft destined for this Grand Tour, later famously christened Voyager 1 and Voyager 2, were on the cusp of being transported to Cape Canaveral for their final launch preparations when news arrived, sobering and urgent, regarding Jupiter's incredibly harsh radiation environment. Pioneer 10, despite its resilience, had experienced phantom commands, ghost signals generated by the electron radiation it endured near Jupiter. This posed a significant problem for the far more sophisticated Voyager probes with their complex systems. What could they do? It was a scramble, a quick rethink, wasn't it? The solution, born of ingenuity and urgency, was surprisingly humble. Local supermarkets were unexpectedly stripped bare of their ordinary kitchen-grade aluminum foil. Yes, that's simple. reflective sheet that wraps your leftovers became a last-minute shield, carefully layered around critical cables within the Voyagers. Without this swift, almost quaint alteration, electrical pressures, up to 40,000 volts, would have surged through the spacecraft's delicate subsystems as they navigated Jupiter's potent radiation belts. Imagine the quiet relief as this simple fix was implemented, ensuring these mechanical dreamers could continue their journey. So, in August of 1977, Voyager 2 began its long outward journey, tracing a path that promised visits to Jupiter, Saturn, Uranus, and Neptune, a true grand tour of our outer solar system. Just 16 days later, Voyager 1 followed, its trajectory slightly different, faster, allowing it flybys only of Jupiter and Saturn, along with various fascinating moons. Both spacecraft were, at their time, the most sophisticated probes ever launched. Marvels of human engineering built to venture into the vast, cold, and lonely distances beyond the sun's comforting warmth. Because they were journeying so far from our star, solar panels, typically reliant on the sun's rays, simply wouldn't suffice as a power source. Instead, these remarkable craft were equipped with what are known as radioisotope thermoelectric generators, or RTGs. These clever devices harnessed the steady, dependable heat generated by the natural decay of plutonium-238 to produce the electricity needed to keep them alive and communicating across the unimaginable stretches of interstellar stretches of its immaterial spether, if you will be pukend, in prucat, in a sen of pen of perkia of stabilio. Diagam pupa via bada quip by white do you out with death but the blues I was it's a subtle warmth, a contained power, allowing these silent explorers to whisper their discoveries back to us. As Voyager 1 finally approached Jupiter in January of 1979, the images it began to transmit were nothing short of breathtaking. Sequence after sequence revealed a planet of astonishing complexity and dynamic energy. The gas giant's famed Great Red Spot, long observed as a blurry patch from Earth, was unveiled in exquisite detail as a colossal, swirling, rotating storm, larger than our entire home world. It's a marvel, isn't it, to finally see such a legend clearly. Back in 1665, Giovanni Cassini had first described a permanent spot, regularly observed into the 1700s. But it wasn't until the late 1800s that it was depicted as red. Yet, even now, we wonder if those historic observations referred to the very same feature, or merely a phenomenon that periodically erupts in Jupiter's tumultuous atmosphere. Voyager 1 made its closest approach to Jupiter early in March of 1979, and as the probe neared, the activity at NASA's Jet Propulsion Laboratory intensified, becoming a frenzy of data reception and analysis. This was the rhythmic pattern of the Voyager flyby missions: long, quiet, almost meditative cruise phases between the planets, followed by these electrifying, brief periods when a torrent of information from the spacecraft would utterly overwhelm the dedicated researchers back on Earth. Sometimes the quiet moments prepare us for the greatest revelations, don't they? One of the most profound contributions made by the Voyagers was the complete transformation of our understanding of Jupiter's Galilean moons. Previously, they were mere distant dots of light in even the best telescopes. But now, through Voyager's eyes, we saw that Jupiter's 4 largest moons were each distinct, unique worlds, entirely different from one another. It was like suddenly seeing a family of individuals, where before there had only been a hazy group portrait. The first surprise arrived in the form of Io, the innermost of these fascinating satellites. Its surface shimmered with a sulphurous yellow hue, and one particular long-duration exposure revealed an utterly unexpected plume erupting from its surface. Instead of being a cold, geologically inert world, as many had supposed, the immense gravitational squeezing Io receives from its giant neighbor perpetually heats the moon's interior, making it a surprisingly active place. That plume, stretching hundreds of kilometers above the surface, was a direct testament to a powerful volcanic eruption, a vivid splash of life in the quiet void. Just 3 months after Voyager 1 had moved beyond Jupiter, in July of 1979, its twin, Voyager 2, made its own closest approach. This allowed it the opportunity to examine different moons even more intimately than its predecessor. Europa was the next revelation. Highly reflective, its surface appeared incredibly smooth, perhaps the smoothest of any body in our entire solar system. Further detailed observations unveiled mysterious pressure ridges, eerily reminiscent of the grand polar ice flows we see here on Earth. Europa, it turned out, was a frozen world, but one with a profound secret, a vast, hidden ocean believed to lie beneath a thick crust of ice, heated, much like Io, by the relentless tidal flexing from Jupiter's immense gravitational embrace. As Voyager 2 continued its onward journey towards Saturn, the planetary researchers back home were left with colossal amounts of raw data about Jupiter, still waiting to be processed and understood. The Voyager missions had provided us with a fundamental, revolutionary view of the Jovian system, yet, as is often the case with truly profound exploration, they had ultimately raised far more questions than they were able to answer. It would be more than a decade before Jupiter would receive another visitor from Earth, another silent ambassador seeking its secrets. That next visitor arrived in October of 1990, when the Space Shuttle Discovery gracefully lifted the European Ulysses, SPAC ECRAFT, into low Earth orbit. From there, Ulysses was boosted onto its primary mission to observe the Sun. But first, it too would have to pass Jupiter. You see, all the planets generally orbit the Sun in the same direction and roughly within the same plane. A celestial racetrack we call the ecliptic, formed from the spinning disk of dust and gas that birthed our solar system. The designers of Ulysses, however, wanted a unique perspective. They longed to see the Sun from an orbit above its poles. And this is where Jupiter, once again, played its colossal part. The giant planet's extreme gravitational pull was precisely engineered to bend Ulysses's flight path, essentially kicking it out of the ecliptic plane. This allowed the probe to begin making its unique north-south orbits of the Sun, gazing down upon our star's mysterious poles. Isn't it just like space to find elegant solutions in the most powerful forces? Ulysses wasn't the only probe to harness Jupiter's immense gravity in such a clever way. Both the Cassini probe, bound for Saturn and launched in 1997, and the New Horizons probe, launched in 2006 on its epic journey to Pluto, were able to shave years off their flight times thanks to carefully choreographed Jupiter flybys. Each of these probes also managed to make meaningful observations as they whizzed past the benevolent giant, adding to our ever-growing cosmic atlas. Meanwhile, back in the pristine, clean rooms of the Jet Propulsion Laboratory, another new probe was quietly taking shape, Galileo. This spacecraft was designed to be a game-changer, the very first to actually go into orbit around Jupiter, to live and breathe in its immediate vicinity for an extended period. Its massive 4.8-meter antenna, crucial for sending back its precious data, was folded up tightly like a delicate umbrella, meant to deploy only once it was safely on its way to the distant gas giant. Though originally scheduled to launch in 1986, it sadly sat in storage for years, a silent testament to human tragedy after the Space Shuttle Challenger exploded. But its time finally came. Galileo launched aboard the Space Shuttle Atlantis in October of 1989. However, new rules governing shuttle launches meant a change in the booster used to propel Galileo out of Earth orbit. The less powerful solid-fuel upper stage, now mandated, couldn't send Galileo directly to Jupiter. Instead, it ingeniously redirected the probe toward Venus for an initial gravity assist. This new, altered flight path meant Galileo would be traveling through a hotter region of the solar system than originally planned. A crucial decision was made to keep that heat-sensitive antenna furled, tucked away, and protected until after the spacecraft had looped back past Earth for another gravity assist. Galileo made too. You feel a gentle shift through the hull beneath you, a barely perceptible tremor that signals our quiet drift through the cosmos. Long ago, another vessel, Galileo, played a delicate game of celestial billiards, making several close passes of our home world, Earth, each time gathering a little more speed, a little more momentum for its grand journey. Its first swing by was a crisp December morning in 1990, well over a year after it first left the launch pad. The faint hum of our own engines is a comforting backdrop as you imagine the quiet anticipation of those early days, the careful calculations of trajectories. Another year slipped by in the silent vacuum of space, and as Galileo approached Earth once more, a small complication arose. Its vital, high-gain antenna, meant to unfurl like a giant umbrella for clear communication, was only partially open. For months, engineers back home tried every trick they knew, sending commands across the light years, attempting to coax the delicate mechanism open. They eventually realized that prolonged storage had caused the tiny lubricants at the antenna's rib tips to simply vanish. A quiet sigh of disappointment, perhaps, but a resilient team simply adapted, relying on Galileo's smaller antenna, accepting that information would trickle back to Earth at a much slower, more deliberate pace. Isn't that just like space, always throwing a curveball? As it cruised patiently towards Jupiter, Galileo also became an intrepid explorer of the asteroid belt, encountering several rocky wanderers. Among them, it gave us our first intimate look at Ida, a truly special asteroid, unique because it harbored its own tiny moon. You can almost see the console lights shimmering with the new data, a silent wonder unfolding on the screens. Then, in July of 1995, still half a year from its grand rendezvous with Jupiter, Galileo released a small probe, a brave little messenger designed to plunge directly into the gas giant's swirling atmosphere. Imagine that tiny probe, a silent bullet, diving into the swirling tempest of Jupiter, its mission to taste the very air of the giant. For a tense, exhilarating hour, it held on, diligently sampling the atmospheric composition. The data flowed back to Galileo, recorded for its eventual relay across the void to Earth. What did it find? Hardly any water vapor, which was quite the surprise, along with far lower levels of elements like helium than anyone had predicted. The probe also reported dizzying extremes of heat and cold, hinting at intense energy bubbling up from the planet's mysterious interior. Such a brief, daring journey, yet so many revelations. Barely an hour after that courageous probe fell silent, its transmissions ceasing, Galileo himself began its perilous orbit insertion burn. A deep, resonant thrum likely vibrated through Galileo's entire frame as its engine ignited, a ballet of controlled power that had to last an astounding 49 minutes. This monumental effort was designed to sling it into a highly elliptical, equatorial orbit around the colossal gas giant. But even this wasn't the final destination. This initial path would be carefully adjusted with a second, crucial burn at its highest point. The mission designers, you see, were acutely aware of Jupiter's incredibly harsh radiation environment. This second, precisely timed engine burn was essential, a careful maneuver to lift Galileo higher, nudging it above the most punishing radiation zones that hugged Jupiter's closest approaches. You can feel the subtle G-forces as our own ship makes minor adjustments, a reminder of the constant dance of physics. Galileo's initial looping path eventually brought it breathtakingly close to Ganymede, Jupiter's largest moon. During this period, the engineers faced yet another challenge, trying to diagnose damage to the spacecraft's vital tape recorder, with the main antenna crippled. This recorder was absolutely critical for storing and slowly replaying the precious data gathered during its brief, intimate encounters. The tape recorder, a seemingly mundane piece of equipment, had become stuck in rewind for 15 agonizing hours, its delicate tape degraded by the relentless cosmic rays. Even the tiny light-emitting diodes, crucial for its control, had started to acquire radiation defects. Despite these mechanical woes, Galileo pressed on. Its second orbit also brought another close pass by Ganymede, and this time, Galileo made a truly groundbreaking discovery. Ganymede is the only asterisk moon in our entire solar system with its own significant magnetic field. And as if that weren't enough, it also harbors a vast, salty ocean, nestled secretively between two layers of ice. Fascinating, isn't it? Galileo's subsequent orbits were subtly varied, a deliberate dance to allow it to make close approaches to a variety of Jupiter's captivating moons. However, these very equatorial paths, designed for intimate rendezvous, inevitably plunged the spacecraft through Jupiter's most intense radiation belts, those hotspots that pulsed with unseen energy. From the earlier Voyager missions, the moon Europa had already sparked considerable interest, and Galileo's observations only intensified that curiosity. Data from multiple instruments converged, confirming the tantalizing presence of a salty ocean hidden beneath Europa's icy crust. Later, a deeper dive into Galileo's data revealed even more astonishing secrets about Europa, showing plasma wave and magnetic field information that pointed to plumes of water vapor erupting from cracks in its frozen surface. Think of it. Europa holds more water than our own Earth, making it a compelling candidate for harboring life beyond our world. Then there's Io, already a known volcanic hotspot, but Galileo observed something even more dramatic: tides in the moon's solid surface, rising and falling by over 100 meters. The incredible heat generated by this relentless gravitational distortion makes Io's countless volcanoes hotter than anything we've ever seen on Earth for 8 incredible years. Galileo bravely navigated the unforgiving environment around Jupiter, completing 35 orbits and meticulously filling in our limited understanding of the entire Jovian system. This was, by no means, an easy mission. Galileo was a remarkably robust spacecraft, but the brutal radiation constantly stressed every single subsystem. Engineers back on Earth were in a perpetual state of problem-solving, tirelessly devising ingenious workarounds for the frequent breakdowns. Instruments would register increased noise whenever they neared Jupiter, and current leakages, often caused by the radiation, forced several resets of the onboard computer. These computer resets, though necessary, often resulted in the frustrating loss of crucial data. But human ingenuity, as always, prevailed. Clever software changes were developed, enabling the computer to recognize these resets and, miraculously, recover by itself. The hard-won lessons from Galileo were invaluable, directly influencing the design of the next generation of spacecraft destined for Jupiter. And then, a new chapter began, signaled by a countdown that reverberated through time and space. 5, 4, 3, 2, 1, and a powerful ignition, the liftoff of the Atlas V, carrying Juno on its own track to Jupiter. In August of 2011, Juno embarked on its nearly 5-year voyage to the gas giant, a journey that would unfold with a very different set of mission parameters than Galileo's. This new explorer would intentionally ignore Jupiter's alluring moons, focusing its gaze exclusively on the planet itself. Its design was revolutionary. Crucial electronics were meticulously shielded within a thick, protective titanium vault, a secure sanctuary against the harsh radiation. And instead of relying on a plutonium power source, Juno would harness the sun's distant energy with massive solar panels. The sun's intensity out at Jupiter is only about 5% of what we experience here at Earth, which explains why Juno's solar panels are truly enormous, stretching out like magnificent wings. A global shortage of plutonium-238 had necessitated this change in power source, nudging innovation forward. Juno followed a long, looping orbit, first venturing beyond Mars, then gracefully swooping back towards Earth for a crucial gravitational boost. This maneuver, a cosmic slingshot, added a staggering 14,000 kilometers per hour to its velocity, launching it onward, directly towards Jupiter. You can almost feel the added momentum, a silent push into the deep unknown. Juno approached Jupiter on a carefully calculated path that took it high above the planet's north pole. Its destiny was a unique north-south orbit, a clever strategy designed to keep it largely clear of the most severe sections of Jupiter's fearsome radiation belts, which stretch outwards from the planet's equator. 4 days before its closest approach, a command silently traveled across the vast distances from mission control, initiating the craft's autopilot. Then, on a momentous July 4, 2016, Juno began its own engine burn, a precise deceleration maneuver that would gently insert it into a 53-day orbit around the colossal world. 48 minutes later, back at Mission Control JPL, the first reassuring tones were received, verifying that Juno had indeed begun its critical deceleration. What a tense 35-minute wait that must have been for the system's engineers, every second stretching into an eternity before the final, sweet confirmation came through. Juno had performed its intricate ballet of propulsion exactly as intended. You can almost feel the collective sigh of relief, can't you? A silent cheer echoing across the void, a testament to years of meticulous planning and unwavering dedication. For the Juno scientists and engineers, it was an immense relief. Things were proceeding precisely according to plan. You see, Juno is equipped with an extraordinary suite of instruments specifically designed to pierce through Jupiter's incredibly thick, swirling clouds. Its unique polar orbit allows it to meticulously compile a three-dimensional map of the upper atmosphere, gradually building a comprehensive picture of the entire planet as it majestically rotates beneath. The very first images of Jupiter, captured from this fresh, new perspective, were utterly breathtaking, appearing as if they belonged to an entirely different world. Researchers were, quite simply, stunned. The initial plan was for Juno to complete just 2 of these longer 53-day orbits, before transitioning into a series of much shorter 14-day orbits. That you're drifting here with me, aren't you? Feel that faint hum of the ship, a steady pulse in the quiet. Our little explorer, Juno, depends on its engine, fueled by a delicate, spontaneous mix of hydrazine and nitrogen tetroxide. The propellant is pushed by a bladder of expanding helium, a gentle breath in the void. But as Juno completed its second majestic orbit, those helium valves had a tiny, fleeting moment of stubbornness, a quick decision. No need to rush. Let's maintain the original, longer, more contemplative orbits. The mission received a lovely extension, allowing for this slower, grander dance. Sometimes, the universe just asks for patience, doesn't it? Barely a day later, a different kind of quiet descended. Juno slipped into safe mode. All instruments went offline. A sudden hush, and data, for a moment, simply vanished. It was a familiar echo, reminding some of Galileo's past struggles. But our brilliant engineers, peering across the light years, swiftly traced the issue, not to the core, but to a minor data transfer hiccup from a single instrument, a small whisper in the cosmic conversation, nothing more. And so, our distant scout remains healthy, a quiet guardian in the vast, cold dark. Just a temporary pause, a deep breath. Now, let your gaze drift beyond our faint console lights, towards that distant, swirling jewel, Jupiter. Its majestic axis tilts only a shy 3 degrees, making its poles almost impossible to truly see from our usual vantage, until Juno, our plucky vessel, gave us an unprecedented, direct view, and oh, the secrets it unveiled. Through infrared eyes, we saw not calm expanses, but intricate tapestries of storms, swirling and dancing at both poles. A truly mesmerizing, chaotic ballet, wouldn't you say? At Jupiter's North Pole, a grand central vortex, deep and brooding, is encircled by 8 smaller, whirling anticyclones. Like a celestial guard, they spin. And at the South Pole, a different pattern emerges. 5 powerful anticyclones gracefully orbit their own central tempest. Here's the truly baffling part. All these colossal storms, rotating in the very same direction, yet they don't obliterate each other. Why? Scientists are still pondering this cosmic enigma. Isn't that just like space, presenting such elegant, baffling puzzles, inviting us to wonder? Imagine our ship, ever so gently, nudging through the solar wind, with Juno making its 7th daring close pass. This time, a special rendezvous, a direct flight right over the legendary Great Red Spot. You can almost feel the titanic pressure, the sheer scale of it, can't you? Juno's clever microwave radiometer, like a painter's brush, mapped the storm's fiery heart, charting heat distributions through varying layers, plunging an astonishing 350 kilometers deep into its churning depths. And what did it find? Much, much higher temperatures radiating from those profoundest levels it could touch. This isn't just a surface swirl. It's a colossal, incandescent furnace beneath the clouds. Unlike our Earth, with its mountains and continents to eventually slow down the mightiest storms, Jupiter offers no such resistance. There are no geographical features, no friction to wear them down. So, these storms, once born, simply rage on, almost eternal. The great red spot, this ancient, angry eye, holds its position steadfastly, roughly 22 degrees below the equator. Yet, mysteriously, even this colossal vortex seems to have journeyed around the entire planet at least 10 times since we first began reliably watching it. A paradox of stability and wanderlust, isn't it? Such a grand, bewildering dance in the cosmic ballroom. Now, let's consider something truly immense, something you can almost feel stretching out into the void: Jupiter's magnetosphere. It's truly colossal, a vast, invisible shield, trapping charged particles in shimmering bands that extend to unimaginable distances. For delicate electronics on orbiting spacecraft like Juno, this is a formidable challenge, like navigating a storm of invisible energy. You can almost hear the faint static crackle in the cosmic silence. For so long, we assumed Jupiter's magnetic field was born like Earth's, deep within, through a dynamo action, the swirling convection of electrically conductive fluid. A neat, tidy theory, right? But Juno's profound whispers from the deep suggest otherwise. Its findings paint a picture of a lumpy magnetic field, hinting not at a core dynamo, but perhaps an atmospheric source, something utterly different. And those giant, ethereal auroras, dancing in vibrant curtains at Jupiter's poles, they, too, seem to ignite from a different spark, a mechanism distinct from our familiar terrestrial light shows. It's like discovering a whole new way the universe performs its magic. By meticulously studying the gas giant's pristine composition, researchers hope to unlock secrets from the very dawn of our solar system. Earth, forever reshaped by tectonic shifts, tells one story. But Jupiter, vast and largely untouched, is thought to be a true time capsule, preserving the exact essence of the primordial cloud of gas and dust from which our entire cosmic neighborhood was born. A living fossil, floating serenely in space. You might need a moment to just float here and ponder that. Every grand journey eventually finds its culmination, and for Juno, its ultimate destiny is a final, noble sacrifice. At the mission's close, our intrepid scout will be gently guided on a collision course with Jupiter itself. A necessary, poignant end, designed to meticulously avoid any possible contamination of Jupiter's delicate, pristine moons. We wouldn't want to accidentally introduce terrestrial microbes to potential alien ecosystems, would we? It's a profound respect for the unknown. But even as one chapter closes, another is already stirring in the cosmic winds. The very next grand endeavor for the Jovian system sets its sights on Europa, that tantalizing, icy moon. Many believe it holds the greatest promise, after Earth, to harbor some form of life beneath its frozen shell. This ambitious new explorer, aptly named Europa Clipper, is poised to launch soon. Like Juno, it will draw its life from the sun's distant embrace, powered by solar arrays. Its elliptical dance around Jupiter will bring it soaring over Europa every 2 weeks, a relentless search for clues. Early whispers of the mission even envisioned a small lander, a direct touch, but that idea was wisely put aside for now. We simply need to learn so much more about that enigmatic, icy surface first. Patience, my friend, patience. Europa's ice crust is believed to be a formidable barrier, perhaps at least 19 kilometers thick, a truly immense, frozen shield. But to truly understand what lies beneath, meticulous, accurate measurements are paramount. Imagine, if we could pinpoint even slightly thinner areas, small windows in that icy expanse, future missions might then dare to penetrate, to finally access the vast, hidden ocean that shimmers beneath. The possibilities are truly breathtaking, aren't they? Concepts for ingenious underrise explorers are already taking shape in the minds of our most visionary engineers, dreaming of submersible craft navigating alien seas. And rest assured, we can anticipate many more dedicated missions focusing on other fascinating moons throughout the solar system. Because, ultimately, all these journeys lead us back to the colossal heart of it all. Jupiter, as the largest planet, its influence on the very fabric of our solar system is profoundly undeniable. It holds more than twice the mass of every other planet combined. Think of that for a moment. Every single other planet's orbit, even ours, is subtly, perpetually guided and affected by Jupiter's immense, silent gravitation. A true cosmic shepherd, indeed. In our quest to understand Jupiter, and indeed the very essence of our cosmic home, we've sent our curious robotic eyes to many planets. But some worlds have felt our touch less frequently than others, shimmering far away in the vast darkness. Take the outer gas giants, for instance, Uranus and Neptune. They are so incredibly distant, isn't it true? Like whispers on the very edge of our solar system, making them incredibly difficult to reach. Uranus floats 20 times further from the Sun than our own Earth, while Neptune, even more remote, is 30 times further still. Imagine that journey. Only one brave emissary, NASA's legendary Voyager 2, has ever had the privilege of seeing both these icy titans up close. A truly solitary sentinel. Then, consider the opposite extreme, Mercury. It's cradled so intimately close to the blistering heart of our Sun that any probe we send must embark on an elaborate, circuitous dance, like a cosmic ballerina, just to counteract the Sun's immense, hungry gravitational embrace. Mariner 10, a trailblazer, gracefully flew past Mercury back in 1973, offering us fleeting glimpses. Then, decades later, the Messenger probe achieved an even greater feat, finally slipping into orbit around that sun-baked world in 2011. Each journey a testament to our enduring curiosity. Then there's Venus, our closest planetary neighbor, deceptively near and seemingly easier to reach. Yet, it presents its own unique set of formidable challenges. Its entire surface is shrouded by an impenetrable veil of dense, shimmering clouds, hiding its features from our prying eyes. And beneath those clouds, conditions so utterly hellish, so incredibly oppressive, that they defy imagination. You can almost feel the searing heat through the thick, acidic atmosphere. The brave Russian Venera craft managed to touch down, but in that unimaginably hostile environment, they could only endure for mere minutes before succumbing. A fleeting glimpse of a truly alien landscape, but Venus offers a different kind of celestial spectacle, a rare and exquisite alignment. Roughly twice every century, this veiled planet gracefully passes directly between our Earth and the Sun, an event known as the Transit of Venus. It was observed with immense dedication in 1769, a pivotal moment in scientific history. Those early astronomers, with their painstaking observations, realized that by carefully timing Venus's slow, measured passage across the Sun's radiant face, they could precisely calculate the exact distance to our star. And that, my friend, was a key that unlocked something profound. Far more accurate methods of navigation, setting sail for a clearer understanding of our universe. A moment of true brilliance.